So welcome to this last presentation of the day, of the conference. As mentioned, this session will be split up into two parts. First, I will be talking about the challenges that IXPs face in their network and how EVPN can bring a solution there. And then in the second part, Dr. Thomas King, who is the CTO of DE-CIX, will talk about their experiences with how they implemented this already in their network. So some of you might still think that IXPs is a bit niche, but when you take a look at the Internet Exchange table, Internet Exchange map, you can see that there's actually over hundreds of IXPs all over the world. Some of them are small, some of them are really big, like in the case of DE-CIX, who are connecting over 1,000 autonomous systems and have presence in more than 40 countries. So what does an IXP or an Internet Exchange provider do? They interconnect, excuse me, they interconnect service providers, content delivery networks, and other internet infrastructure companies so that their clients can communicate directly with each other. They can exchange routes, they can exchange data directly, thus reducing latency and cost. Okay? So their customers are connected in one big, in the case of DE-CIX is the /21, I think, subnet, and also so they share the same broadcast domain, which means that any bum noise will be hitting all the peering routers that are connected to it. This is a problem, of course, so they want to keep bum noise down as much as possible. That's why they implement strict filters. Now, you can't filter everything. For instance, protocols like ARP and D are still necessary because you have to learn the MAC address of the peers that you want to set up a BGP peer with. Now, ARP and ND can be very impacting to routers because it's handled typically high priority and slow path, so it hits the CPU of the router. And there have been instances where the disappearance of a group of peering routes because of power outage or whatever actually triggers an ARP storm in the IXP network, and this ARP storm then took down other BGP peers, thus resulting in a major outage of the IXP. So we need to avoid this. We need to find a way to contain ARP and ND messages in the network. Now, EVPN can help here. You already know that EVPN offers nice features like control plane learning, single active, all active multi-homing, loop protection, a wide variety of data plane encapsulation options, etc. But the original EVPN RFC also mentioned that a PE can not only learn and distribute MAC addresses to other PEs, but it can also learn the associated IP addresses. So with this information, you form MAC IP combinations and send them over to the other PEs with the MAC IP route, the RT2 EVPN type. And then the PE nodes in the EVPN network, they can build up a proxy ND or a proxy ARP table so that they themselves can reply to ARP requests coming from their peering routes that are connected to them. And there's no further need for for ARP messages or for ND messages to be sent into the IXP network. So this is a very nice solution. But the original RFC of EVPN was a little bit, well, it didn't contain a lot of details on how to do this. Plus, it didn't also not cover all use cases, like for instance in IPv6 ND, you also have flags for indicating whether this is a router IP or an Anycast IP. There simply is no way to conveying this information in the MAC IP router sent to the other PEs. Nor is it possible to indicate whether a MAC IP combination has been learned locally dynamically or whether it was configured statically. So we need a way to convey this information over the signaling. Now, RSC 9047 jumps in here and brings a solution to this in the sense that they added a extended community which will contain this information in the form of bits. You have the I, the O, and the R bits, immutable, router, and override. Immutable means, well, indicates whether a MAC IP combination is static or not. Router, well, that's clear. And override indicates whether it's an Anycast MAC address. And then there's a second RFC, RFC 9161, which now extensively elaborates on how proxy ARP and ND should work on the EVPN PEs. Now, together with these two RFCs, these features, IXPs now have the possibility to deploy maximum security in their network. Since they are operating in a very controlled environment, they know which IP addresses should be assigned to which of them their customers and to which ports they are connected, which MAC addresses they're using. So they can manually construct or send to their management platform the MAC IP list, and they can even also add spare MACs in case that the main link from the peering router goes down. They have a spare MAC. So once you configure all these MACs and IPs and assign them to ports, then you don't need to learn anything anymore. So we can switch off dynamic IP MAC learning. And because of this, you can also block entirely the flooding of ARP, CARP, and ND messages. Other than that, there's still the filters, right? You can discard traffic coming from unknown MACs. You can also discard anything that's not IP or ARP ND. Of course, here it's nice if you can have line rate filters, because we're talking about lots of traffic. You can rate limit bump traffic, and you can also introduce sponge MAC. Sponge MAC can be used to reply to any ARP requests for unauthorized IPs, and then it's up to you whether you want to drop traffic destined for this point to this sponge MAC or send it to a remote site, a centralized site for further investigation. So you can see that with this tool set, IXPs now have a very high degree of control over noise in their network. And with this, I would like to introduce Thomas, who will talk about the practicality of implementing this in their network.
Thank you, Sigi, for the introduction already of the topic and the issues which we as internet exchanges face, especially if we run large peering platforms. And I want to highlight that a little bit more in detail in the next few slides, and also how we migrated from our existing MPLS, VPLS setup into EVPN. So before we do that, let me briefly introduce DE-CIX to you. So DE-CIX runs cloud and internet exchanges all over the world. We have 55 locations covered today. In the cloud exchange environment, we connect to more than 50 cloud service providers, so AWS, Azure, IBM, Oracle, Google Cloud Platform, and all the other big guys you most probably know, but also some smaller, more niche ones, which are still very important for us because we can provide connectivity then to our mainly enterprise customers or carriers or resellers or whoever who wants to connect to them. In the internet exchange business, we have connected more than 3,200 networks globally. And in total we have a connected customer capacity of more than 140 terabits. So I think that gives you an understanding on the size of our network. If you look at it in the company itself, we are now 29 years old. We are, you most probably reckon that from the name. DE stands for Germany, so we are started in Germany. If you look at our customer base, and we have here put some logos on the slide so that you can already also categorize our customers. You see that we have different segments which we serve. I would say mainly all the big companies in the internet are connected to us. If your logo is missing and you have a pricing, peering or cloud connectivity issue, please come and see me and we can talk about how we can support you guys solving that. So, but now let's switch to the challenges of running large peering LANs. Sigi already talked about some of the issues, mainly from the robustness and security side of things. I want to highlight that a little bit more into the details and then talk about the solution of EVPN. So let me start with DE-CIX Frankfurt, because that is the biggest internet exchange which we run. It has more than 1,100 networks connected nowadays. And of course, we see a lot of peering sessions with our route servers. Some of the customers even run more than one. So in total, we have 1,300 peering sessions with the route server. In total, we have about 14 terabits of peak traffic. Usually when there are Champions Leagues, soccer games, on Tuesdays, when it's free on Amazon Prime for subscribers, we see new traffic peaks. So this is what we see at DE-CIX Frankfurt. If you look at DE-CIX New York, it's a similar picture. It's a little bit smaller, but still quite massive. 260 networks connected, and roughly 1.3 terabits of traffic, which we push at this location. Now let's look a little bit deeper into the boom traffic, because that was already mentioned as an issue, right? And this is a graph from DE-CIX Frankfurt, where you can see that the boom traffic mainly generated by ARP and Neighbor Discovery is in the range of 2 megabits. And that's a lot of packets which need to be processed by the CPU. And now you could say, okay, there's enough CPU power, so what's the issue? No, it's not the case. As Stig already mentioned, it takes a lot of CPU power, and some of the vendors, especially one a big vendor, they had issues handling this large amount of packets in the default configuration. So when customers were putting this gear into our peering LAN, they had struggles getting it to work, so they needed to do changes, and this is not something we want to cause, so we wanted to get rid of this. We wanted to solve that issue. So how did we do that? So we were coming up with Peering LAN 2.0 that is mainly introducing EVPN with ARP and Neighbor Discovery proxies, as Sigi just mentioned. We added a few more things to that. When you touch the network, a big scale, you want to improve on other levels as well. So we were introducing BFD on our global network links, and also we were cleaning up our MPLS tunnels, and now we use LDP and SVP only. But I will only focus on the EVPN topic here in the next slides. So, when you need to migrate a network in the size which we run, you really need to think what you do. And we were considering different scenarios. What could we do? Could we go router by router, or should we do location by location, or should we do service by service? So with service, we mean a peering LAN, but please remember that we have remote peering nowadays as well. So even if we talk about a peering LAN like DE-CIX Frankfurt, that is also available in New York. So meaning that not only the routers in Frankfurt at the location in Frankfurt need to be touched. If you move or if you migrate a service like this, you need to also touch the routers which provides remote peering at other locations to Frankfurt. So that were the scenarios we were looking into, and then we came up with KPIs so that we can measure what is the best solution to come up with. So what we wanted to do first, we wanted to come up with small steps, with gradual steps, which you could easily control and roll back if something goes wrong. So that was one dimension, and handling complexity is always hard, right? So you want to have something which is not too complex, because if it's too complex, you don't understand it, you can't control it, you can't manage it. And the most important thing, of course, was for us, if you do a migration like this, you want to make sure that the downtime your customer's experiencing is as low as possible. And actually, that was the main driver for selecting the scenario that we go router by router, service by service. So meaning that we do peering LAN by peering LAN during this migration. Though, how do you prepare for a migration like this? So it all starts with testing. And of course, we went into our lab, right? We were rebuilding parts, critical building blocks of our network in hardware in our lab, so that we could do lab tests with hardware on hardware. But this is only, I think, the not so critical part, because what we also did is, and I think that was contributing most to the quality of the migration, is that we emulated the complete network in software. So we are running only on Nokia gear, so we are using the virtual routers from Nokia as software components, and then loaded the complete configuration which we had during the MPLS, VPLS setup into this software routers. And then we were creating test cases. So we were really doing, this is the input which we have. This is now not an MPLS, VPLS configuration which we need anymore. We need to have an EVPN configuration. This is the output of the configuration. We deploy that to the routers and then test the services. Do they behave as we expect them to behave? And we found a lot of interesting stuff. Let me highlight two things. Of course, you find all the manual configuration which you just want to do once to fix something or debug something and then forget forever. And you also forget, or you also find hardware which you borrowed from your vendor for, an issue. Actually, we found one line card which we never gave back. We fixed that by now. Yeah. So that is also true, that you sanitize your network if you do things like that. Yeah, and in the end, as I said, with the config generators and testing of them, really like software unit testing, you could really produce a very clear quality, because you have a clear understanding of what the output will be. But this is only one part of the story, right? Though then you have the proper configuration, but you also need to change your automation tool chain, because our network is fully automated in terms of how we deploy services for our customers. So we needed to do two things. We needed to change the data sources where we, describe how services need to look like. So we need to make them EVPN aware. So data peering LAN now needs to be based on MPLS or VPLS, or does it need to be based on EVPN? Yeah, so we need to change that, and of course all the software tools in between, which then in the end create the configuration. So we are doing a lot of changes there as well, and of course also a lot of testing. Because again, if you touch all of your customers for migration, every single customer, you want to make sure that you just do it once and you do it right. So this is what we did. We then started the migration, beginning of November, 1st of November. And we started with DE-CIX Phoenix, the peering LAN over there, because it's a very simple setup, one of the simplest setups we could find in our network. So we did that during a maintenance window. In a very short time, a few seconds, customers were experiencing downtime. And then we were waiting for a week to see during the burn-in time, are there any issues coming up? Either customers report issues or we see issues on running the network. But luckily that wasn't the case. So we moved on, from very small to the biggest. So we moved on to Frankfurt, because we were saying if we have a proper understanding that our migration tools work, let's go to Frankfurt and touch that one. And we did that. Then as a second migration, which worked very, very well as well. and then we were doing migrations on a weekly basis. And 28 days into the migration, we mainly migrated all of our peering LANs, especially in the US. There were a few in Europe still left. And then 44 days into the migration, we actually finished the migration, also including all the Cloud Exchange related features which we run, like direct cloud and closed user groups. So we migrated the whole network into EVPN and, you know, as I said, the peering LAN 2.0 features, which I just showed you earlier. So now what is the result? You remember this graph, right? This was one of the slides I showed you before, the boom traffic in Frankfurt, mainly generated by ARP and Neighbor Discovery. And on the first part of this graph, you see the same levels, nearly 2 megabits of traffic for this boom traffic. And then you see the time when we did the migration, and then you see the traffic coming back. But now it's only 1/4 of what it was before. So now with the peering LAN 2.0, we clearly see that the boom traffic is on a different level. And that's the overall network view. If you look at it from a customer perspective, it even looks better, right? So on the left-hand side, you see the flood and learn from the MPLS VPLS setup. You see that customer routers were hit by nearly 2,000 packets a second. And then when we switch to peering LAN 2.0, they see less than 65 packets a second. So that's a big change. And also our customers were saying that on social media. So here I have a few posts from customers talking about this change and what they experience on their CPUs. That was definitely also visible to them, and actually it triggered alarms for them, so they picked it up in the middle of the night. We got a lot of congratulations from our customers, which is a big thank you to the team which made that happen, because the migration went very, very smoothly, nearly to perfect. So that is exactly what you want to see. Yeah, that brings me to the end of my presentation. Let me summarize what we just saw. So with EVPN features, large peering LANs can run securely, efficiently, and robustly. And I just can, underline that that is a big change for us and also for our customers, of course. And then by testing it deeply, that allows you to do this kind of migrations very efficiently and with a minimal customer downtime. And this is what's most important for us, right? So we want to make sure that this works very well. Yeah, that's pretty much it from my side. Do we have time for questions?
Yeah, do we have any questions?
If you're shy talking in this round and you still have questions, please come and see me. I will be around here. Would be great to talk to you guys. Thank you.